All right, so today we're going to talk about the derivatives of exponential functions. Now, before we get started here, I would like to do something that's going to help us later. So, you don't have to write this down. I just wanted to kind of pull these questions out so that when we use these things later, we're not overwhelmed with a lot of rules. So in your homework, over a week ago, I asked you to talk about e's and natural logs and simplifying some exponential expressions. And I think one of them I asked you to do was like e to the natural log of 7. And some of you used your calculator, some of you asked about it in class. The answer to that one is 7. E to the natural log of 7 is just 7. E to the natural log of 4 is just 4. E to the natural log of 29 is just 29. The idea is, and we can certainly prove it, e's and natural logs undo each other. Natural log means log base e. So it's like raising it, right, e to the something, but then log base e, they undo each other. So when we see e to the natural log of x, it just simplifies to be x, okay? All right. Let's talk about simplifying this one. When I see the natural log of a to the x, let's use that power property for logarithms, and let's bring that power down in front, and we have x times the natural log of a. So that's really all I want to do with that one. So we're going to come back to that. I just thought maybe if we started with that, it might help us later. So I'll pull this back out in a minute. A few minutes. Okay. So let's start with e to the x. Remember, e is just a number. It's close to like 2.7, right? Shy of 3. So e is just a number. So it's like we're graphing 2 to the x, 3 to the x, 5 to the x, 10 to the x. It's an exponential function. So I've used a computer to graph this one for us. And I would like us to sketch its derivative. Think about spaghetti, right? Let's even pick a few points here. Maybe I pick this point. And maybe I lay down a tangent line. Gosh, I couldn't have drawn it any better. It looks like this, it kind of goes up 1 over 1. So I'd say at 0, the slope is 1. Maybe I pick this point here, like x equals 1, and maybe we draw in a tangent line. It goes through this point and maybe this point. Oh, gosh, I don't know, like 1, 2.5 over 1. So I don't know, up 2, 2.5, 3, something like that. I'm making up numbers, I guess. Maybe I go out to negative 3. Ooh, that's pretty flat. That's pretty close to 0, maybe 1/10. Now we could certainly do more of these, but more points. But there's the graph, a sketch of its derivative, and honestly, it looks it looks very close to the original graph. So maybe it certainly looks like an exponential. So I'll write that down. It appears to be an exponential. Maybe the same graph? Maybe. That's a guess. Well, let's investigate that guess a little bit, right? So we see they're close, but are they exactly the same? So I'm going to grab a calculator. You don't have to do this with me. You certainly can. Let's go to a graphing page. And let's graph e to the x, and then let's ask it to graph its derivative. So I'm going to hit tab, and I'm going to go to my templates button, and I'm going to say graph the derivative of, you know what, let's just go ahead and type in f1 of x. So now in red, it's graphing the derivative of the blue graph. And honestly, you can't really see a difference now and get rid of our labels. Let's go to the table. So I'm going to hit, I didn't mean to hit tab, let's hit Control T. And let's look at the table. Right here is the original. And here is the derivative of the original. Look at that. Look at those y values, right? These are the x's all the way to the left. And look at the y's. They are exactly the same, aren't they? I mean, we start getting into some scientific notation. But it looks like the derivative of e to the x is exactly e to the x. That's a big deal. Well, that's the easiest one to remember. The derivative of e to the x is just e to the x. Okay? We'll write it down more formally here in just a minute. What if, though, it's not the parent graph? right? What if it's e to the 2x? Well, let's look at the same thing. So I'm going to get rid of my table, and I'm going to go change that first function. What if it's e to the 2x? Is the derivative the exact same graph? Well, no, look, you look at the space in between them. They're not the same. They're close, but it's not exactly the same. So I'm going to go look at that table again and see if we can find that pattern. And maybe I'm going to just go over. But again, these are the original y values, and these are the derivative y values. Let's look at a pattern. That's like 7 to 14, 54 to 108, 109, 43 to 806. I hope we start to see they're doubled, right? The derivative is 2 times the original function. Where do you think that 2 came from? Oh, the chain rule, perhaps? The derivative of the exponent, the derivative of the inside? Yeah, so let's write this rule down and then we'll practice. When you're taking the derivative, we're using u's now, because now that we know the chain rule, any rule that we learn, we're going to incorporate the chain rule. So the derivative of e to the anything will be e to the anything, but then the chain rule says multiply by the derivative of that exponent. The derivative of u we'll call du dx. This is a little more formal than we're used to, but that's because it's going to incorporate the chain rule every single time. So the derivative of any exponential is itself, and then multiply by the derivative of the exponent. Pause that if you need to write that down. Let's go do some practicing. So I've got 4 here. Differentiate. We've got y equals e to the x cubed. It's not just e to the x, it's e to the x cubed, which means we need to use the chain rule. But the derivative of any exponential is itself. So the derivative of e to the x cubed is still e to the x cubed. The chain rule says multiply by the derivative of the exponent. That's it. That's our answer. Let's take a look at the one to the right. We have y equals the sine of e to the 1 over x. Got a lot of chain rules going on here. So on the outside is the sine. So we start with the cosine of e to the 1 over x. That's an e. The chain rule says multiply by the derivative of the inside. The inside is an exponential. We just learned. The derivative of an exponential is itself. So we rewrite the exponential. The chain rule says multiply by the derivative of the exponent. So I rewrote it as x to the negative 1. The derivative would be negative 1 times x to the negative 2. That's it. It's a lot of pieces. Good. Let's take a look at this third one. Y equals x times e to the 4 minus x. We have a product there, don't we? We're going to use the product rule. My first piece is x. My second piece is the exponential. So we've got the first. The derivative of e to the 4 minus x is still e to the 4 minus x. But the chain rule says multiply by the derivative of the exponent, which is negative 1. Finishing the product, we have plus the second, which is e to the 4 minus x, times the derivative of x, which is just 1. We don't have to clean this up, but let's just take a look at what happens when we do. I've got 2 terms here. 1, 2. They both have that exponential. We could factor it out, and that leaves us with negative x plus 1. Or I would prefer to write 1 minus x. I think that looks a lot nicer than what we had. If I said set that equal to 0, you'd have no trouble, right? It looks nicer. So I just factored that out. That was a personal choice. Okay. All right, let's look at this one. Ooh, it looks like we've got a quotient rule. Well, we could, right? There's a quotient. You can use the quotient rule. Or could simplify that first, couldn't we? Right? We're dividing. What if I had like x to the 7th divided by x to the 4th? The rule is we subtract the exponents, right? Same thing, my bases match. So couldn't we rewrite this as e to the sine of x minus x? Subtract the exponents? Oh, I like that a lot already because I won't have to use the quotient rule, but I could. All right, here we go. The derivative of an exponential is itself, so e to the sine of x minus x, times the derivative of the exponent, which is cosine of x, minus 1. Make sure you have brackets or parentheses, right? The derivative of that is 2 terms, so we have to make sure we multiply by that whole thing. That was a choice I made. I chose to simplify first, but I could have just as easily used the quotient rule. It's just going to look a little worse, isn't it? All right. Let's flip it over. So we've just finished talking about e to the x. But what if it's not e to the x? What if it's 2 to the x? What if it's 5 to the x? What if it's 11.2 to the x? What if the base is not e? So we could do a quick little check here on our calculators. Right? Let's just start with 2 to the x. So I'm just going to start a new page, and I'm going to go graph 2 to the x, and then I'm going to graph its derivative. I don't know what its derivative is. I want to see if it's the same. So let's take the derivative of that function that was in F3, not F1. Okay. Are they the same? No, right? Look, they're 2 different graphs there. So it's not the same. It's close, isn't it? It's another exponential. We could try looking at the table and see if we see a pattern, an obvious pattern, right? This is the original, and this is the derivative. I honestly am not sure it's going to stand out to us. So here's what we're going to do. If I want to know what is the derivative of a to the x, and we know the derivative of e to the x, I'm going to take a moment and write this in terms of e's. Okay. Remember how we said e to the natural log of x is just the same as x? So what if I replace that x with something? There we go. I'm going to say y equals e to the natural log of a to the x. I know it looks messy, but e to the natural log of a to the x is just the same as a to the x. So I'm just rewriting this. By the way, you never have to reproduce this. I'm just showing you where the rule comes from. Then I'm going to use our second rule that said if you have the natural log of a to the x, we can rewrite that as x times the natural log of a. So let's do that, right? We have that here. That x comes just in front. So I have e to the x times the natural log of a. I know it seems like we're going in a big circle here. I promise we're doing something. So this is another way to write a to the x. So y equals a to the x can be written as y equals e to the x natural log of a. The reason I did that is so I can take the derivative of this version, because we've just said the derivative of e to the something is itself. So the derivative of e to the x natural log of a is still e to the x natural log of a. The chain rule says multiply by the derivative of the exponent. A is a constant, right? It's a 2 or a 5 or 11.2, which means the natural log of that is still a constant. Let's write that in there. Natural log of a is just a constant. There's no variable in there. So the derivative of x times a constant is just the constant, right? Like the derivative of 2x is 2. The derivative of 10x is 10. So the derivative of natural log of a times x is just the natural log of a. So here's our derivative. Here's our rule. Let's clean it back up. This whole mess right here, remember, was a fancy way of writing a to the x. Again, you never have to reproduce this. I just wanted you to see where this came from. So this is different because it's got an extra piece. The derivative of any exponential, no matter what the base, is going to be the exponential a to the whatever. Then we're going to need times the natural log of the base, so the natural log of a. And then the chain rule says multiply by the derivative of your exponent. So all of this right up here is kind of a proof of this here. You don't have to reproduce this. We're not going to go through these steps every time. It was just showing you where the rule comes from. Okay. Take a moment and write that down. And let's go do some practice. All right, so here we go. I've got 4 derivatives. What is the derivative of 2 to the x? Well, it's itself, 2 to the x. But then we need to multiply by the natural log of the base, so the natural log of 2. That's it. That's the answer. The derivative of 5 to the x is itself times the natural log of the base, so the natural log of 5. Still an exponential, 10 to the x. The derivative is itself times the natural log of 10. Now, we already know this one, right? We already know the derivative of e to the x, but what if we clumped it in and treated it like these? The derivative of e to the x is e to the x times the natural log of the base, or the natural log of e. And what is the natural log of e? It's just 1. Right? So this is kind of like the special version of these 3 up here. Okay. Good. All right, let's do a few more. Throw some chain rule in there. So now it's asking us to take the derivative of 2 to the 5x. There's not just an x there, there's a 5x. So it's an exponential function. The derivative of any exponential is itself times the natural log of the base times the derivative of the exponent, which is 5. That's the chain rule part of it. Okay. Good. Let's take a look at the next one. I've got y equals 4 times x all over 4 to the x squared. Gosh, I don't really think there's not much we can do to simplify this. We could, still not going to get rid of anything. I'm going to go ahead and leave it and use the quotient rule. It's a little bit different than the one on the front because it's not just a 4, it's a 4 times x. So it's not like we can just subtract the exponents. So here we go. Y prime equals, we're going to square the bottom. Oh geez, I already messed up. It's 4 to the x squared. We're going to rewrite the bottom, multiply by the derivative of the top, minus the top, times the derivative of the bottom, which is an exponential, so we rewrite it, multiply by the natural log of the base, and then the chain rule says multiply by the derivative of the exponent. There's my chain rule. Woo-wee! Are there things in there we could simplify? Absolutely. Do I worry about that right now? Not necessarily. Okay, I'll just move on. But to me, that's an obvious simplification, is calling that 8x squared. Right? That's the obvious one. You could call that 4 to the 2x squared, right? We multiply our exponents. So those are just things to think about. Okay. All right. Let's take a look at this next one. D dx. Take the derivative of 3 to the sine of pi x. Overall, I have an exponential function, 3 to the, so I leave it alone, 3 to the sine of pi x times the natural log of the base. The chain rule says multiply by the derivative of the exponent. The derivative of sine of pi x is cosine of pi x. And then multiply by the derivative of its inside, which is pi. Right, so this right here is the chain rule. These other two pieces are just from the rule for the derivative. All right. I don't think we get much out of the last example. Feel free to stop it if you want. I'm going to go ahead and do it, but at this point I think you could probably move on. All right, so on this next one I see a product rule. I have x squared times 10 to the 1 minus x squared. So we've got the first, which is x squared, times the derivative of the second. This is an exponential function, so we have 10 to the 1 minus x squared, times the natural log 10. Chain rule says multiply by the derivative of the exponent, which is negative 2x, plus the second, which is the exponential, times the derivative of the first, which is 2x. That's the answer. That's the derivative. I see two terms. They both have a 2x, and they both have a 10 to the 1 minus x squared. So if you want, you can clean that up. That leaves me with a negative x squared natural log 10 plus 1.